way back in Chapter 8, Section 4, we learned some shortcuts for multiplying special products that allows us to do it a little faster than doing FOIL. So in this lesson, we're going to learn how we can factor those special products. So working backwards from what we did in Section 8.4. Now, if there are only two terms, they are being subtracted, and they are both perfect squares, we can use this method. Now, these are all important conditions. Two terms, subtraction, perfect squares. So here, two terms, 1, 2, subtraction, yes, and 16, h squared, 9, and a squared, yes, they are all perfect squares. So hopefully by now you know the numbers that are perfect squares. As far as variables are concerned, as long as their exponent is even, they are perfect squares. So then it says find the a. Remember, this includes the whole thing. So this whole thing is a squared. So it says find the a by taking the square root of that term. So we have to take the square root of both 16, which is 4, and h squared, which is h. Then we have to take the square root of the second term, so that whole thing is b squared. So we take the square root of 9, which is 3, the square root of a squared, which is a. Now we place a and b in this form. 4h plus 3a, 4h minus 3a. And it doesn't matter if you have the plus in the first parentheses and the minus in the second, or vice versa. You do need one of each, but it doesn't matter which parentheses it shows up in. All right? We'll walk through the same questions on these. So is it a difference of squares? Well, yes, that's two terms. Yes, it's subtraction. However, while 121, c to the fourth, and 25 are all perfect squares, d cubed is not. So we can just write no. We can't factor that using this shortcut. So we just say no and move on. Okay, number 2, this is two terms. There's subtraction, and everything here is a perfect square. So my a, that's the square root of 64, and the square root of g squared. My b is the square root of h squared, which is h. So I do 8g plus h, 8g minus h. Okay, number 3. This is two terms. They are being subtracted, and they are both perfect squares. So we can say the square root of 81 is 9. The square root of c squared is c. So we'll do 9 plus c, 9 minus c. Okay, I'm sorry, I do have a typo here. Hopefully it's correct on your paper, but this is a minus. So this also fits all the requirements once I correct it to a minus. It's two terms, it's subtracting, and everything involved is a perfect square. So the square root of 25 is 5. The square root of y squared is y. The square root of 1 is 1. So you get 5y plus 1, 5y minus 1. Call me crazy, but that method works so well. What if we do it twice in the same problem? I know. So just check this out. If you look at number 5, for example, these are both perfect squares. It's just two terms being subtracted, so it meets all those requirements. So we take the square root of 625, which is 25, and we take the square root of x to the fourth, which is x squared. So we do 25 minus x squared, 25 plus x squared. Now this cannot go any further because it's addition, but this can go further because it's subtraction, and both of these are perfect squares. So focusing just on this one right here, our a is the square root of 25, which is 5. Our b is the square root of x squared, which is x. So this term we can separate further and make it 5 plus x, 5 minus x. This term we cannot separate further, so we just leave it as is, 25 plus x squared. Okay, now number 6 is tricky because you have to remember the very first rule of factoring, which I have not mentioned yet. My fault. If there's anything that both terms have in common, factor that out first. So as I look at 6 and 96, they are both divisible by 6. So I can pull a 6 out, get x to the 4th minus 16. So it's x to the 4th minus 16. I'll need to see if I can use this pattern. They are two terms, they are subtracted, and they are perfect squares. So a is the square root of x to the 4th, which is x squared. B is the square root of 16, which is 4. So the 6 stays. 6 is still part of our answer, but we split this up and we say x squared plus 4 and x squared minus 4. So just like last time, the x squared plus 4 cannot change any. That's done. It's a plus, not a minus, so we can't call it a difference of squares. But this one, we can do the process again. We can say a is the square root of x squared, which is x. B is the square root of 4, which is 2. So that gives me x plus 2, x minus 2. Now, as far as that method with differences of squares, I do think it's helpful. It does make things faster if you remember the pattern, but it's up to you. You can solve this other ways using the other methods that we have or will learn as far as factoring, but I do think this one is worth remembering because it can speed things up. However, just to be honest, this next one we'll learn, I want to teach it to you, but truthfully, it may be easier to do the normal method of factoring to figure this out. So these are perfect squares, but instead of subtraction, they're adding. Well, no, that's not quite true. Sorry. I should just look at what it is. Factoring perfect square trinomials. So if you have a plus b and it gets squared, it gives you this. If you have a minus b squared, it gives you the same thing, except the middle term is negative instead of positive. So I want to show you these, but if after you see these you're like, I'd rather just factor the normal way, I get it. So let's identify what we have. So a squared is our first term. I know I'm dealing with this on number 7. I know I'm dealing with the top equation because it's all positives. It's plus plus. So 4y squared is a squared. B squared is 9. So I can get a by taking the square root of that. Square root of 4 is 2. Square root of y squared is y. For b, the square root of 9 is 3. So then I say, okay, now that I've got a and b, I can just say this pattern right here is equivalent to 2y plus 3 squared. Or if you'd prefer to write it as 2y plus 3 times 2y plus 3, that would be fine too. Either one of those answers is good. So it's not that this method is hard, just honestly speaking, it's a little difficult, especially because of the middle term, to recognize, oh, it's this form. I should use this shortcut. But if you're able to, more power to you, and use it. 8 is using this second one's form, or is in the same form as the second one because we have a minus right here. So I say a squared is 9y squared. So for a, I take the square root of 9, which is 3, the square root of y squared, which is y. This is b squared. The square root of b is 4. So now that I have a and b, I can use this formula right here. So I put a first minus b, and I square it. Okay, last one. What's different about this one? Do you see it? The two things I just gave you have 3 terms. This has 4 terms. So this one is my point of showing you that sometimes when you get in a rhythm, you forget, wait, not everything is in this pattern. So on this one, we want to use the method we learned before, factoring by grouping. So I look at these two, I look at these two, and I put a plus in between, if you remember. So 4 and 7 have nothing in common, but I can pull a squared out of a cubed. So the 4 is left over. I pulled 2 of the a's away, leaving 1 left. The 7 is left over, but there's no a squared because I pulled them both out. Okay, 36 and 63 are both divisible by 9, and since they're both negative, we'll pull out negative 9. Negative 36 divided by negative 9 is positive 4, and we leave the a. Negative 63 divided by negative 9 is positive 7. And lo and behold, 4a plus 7, 4a plus 7, they match. So I can write 4a plus 7, and what's left is a squared minus 9. Oh my gosh, that dastardly teacher. This can't be done anything further, but this one is the difference of squares. I've got 2 terms being subtracted. They're both perfect squares, so I can say a is a, because this is the a squared, this is the b squared, the 9 is b squared. Square root of that is 3. So that one can be fully factored by writing a plus 3, a minus 3. So that would give us our final answer. So I should say there's really 2 reasons I showed you this last example. One is it may not be what you expect in a lesson when you're thinking, oh, well, it's one of these patterns. Well, turns out this one wasn't. However, once we factored it using the factoring by grouping method, we did see there was a difference of squares, which you learned on the front, in which case we did have to use that method to fully factor that.